Don't we? Tonight will be your last lecture. We're covering chapter 10 and 11. That means we're going to talk a little bit about the link state protocol or link state routing, and then we're going to talk about OSPF. Then you will know everything you need to know for that will be on your final. You'll have covered all the information. And so after this class, we have, 3 weeks remaining? Boy, am I good. I've covered 2 complete books. You like that? Going as quickly as I have? Then we'll figure out what to do. I'll figure out what to do while I'm lecturing you in my multitasking mind, which is half asleep right now. So we're going to have a little bit of fun tonight. Get through these, then we'll discuss packet tracers. Let's see. It was 6 and 7 were due this past weekend. Was that correct?
Yes.
And then, so you have 8, 9, and then 10 and 11, right? And then you have your final. So once I grade 6 and 7, then you'll have 9, 10, or 8, 9, 10, and 11 in final. So you'll have 5 grades left in this class. Are y'all super excited?
Bullshit. I'm ready.
Do it?
Bullshit.
For sure. Okay. Let's talk a little bit about link state protocols. We're going to define the basic features and concepts of them. We're going to talk about the benefits and the requirements. Don't ask me why they tell me the exact same thing on the second slide. Anyway, link state routing protocols. We're going to talk a little bit about the Dijkstra's SPF again. And this is also known as the shortest path first. Thus OSPF, open shortest path first. So it finds the quickest way for me to talk to John, and it's going to make that path the easiest way to get there. Okay? We're going to be focusing on OSPF version 2 and the ISIS. We're not going to get into the IPv6 at all in this class, yes.
How do you say that name?
Is this
No,
OSPF?
with the D.
With the D. Oh, Dijkstra's. Okay. Dijkstra's algorithm is also known as the shortest path algorithm, which means we're going to take the shortest path to get from here to here. Or in this case, I think they're going from here to wherever they're going. There's a 20, a 5, and a 2, right? Correct? If I went this way, how long is it going to take me to get there? 10, 10, 20. I'm already at 45, 47. So is this not the shortest path? And that's how they do it. All right. You're going to take the shortest path to the destination that is not necessarily the path with the least number of hops. For example, if this had been a 2, a 2, a 10, what would that be? Not the most hops, but still the shortest path? That's how you figure it out. Okay? Link state routing protocols reach convergence fairly quickly. Once each router learns about its own directly connected network, the link state routers will exchange the hello packet. Hello, Cole. Okay. And then we get that. Then I build what is called a link state packet route. Okay. It basically builds up the information about the bandwidth, the neighbor ID, its link type. Was it T1? Is it a T3? Is it a 56K dial-up? Is it a WAN connect? What type of connection is it? And after the LSP is created, the router floods that information to all its neighbors. So everyone knows if I need to connect to here, you can come through me. Okay? And once they get done with that, they create this topographical map saying who's where. Directly connected networks, you have 2 different types. You have link and link state. A link is the interface on the router itself. Link state is the information about that state of those links. Not to be confused. Does that make sense? So If I say, Kristen, what's the link on the 10 by 100 switch? You would tell me, well, it's a 10 by 100 port. Okay, the link that connects to it, that is going to be a gigabit Ethernet. Okay, that is the link. The link state, is it up? Is it down? What is it? When the protocol sends out the hello packet to it to discover its neighbors, it says, how am I doing? Or, Lee, I'm Scott. What kind of connection do you have with me? A what?
Through a Ethernet.
An Ethernet. We have a slow connection. Brent, what kind of connection do we have?
T1.
We have a T1. Oh, we're getting a little bit better. Todd, what kind of connection we have? Gigabit? Cole, what kind of connection we have?
T3.
T3. We're getting better as we go along. Brent, what kind of connection we have?
What you just call me? Professor Stokely?
Jared, what kind of link do we have? I'm going to do it for the rest of the semester, so don't worry.
I know, that's the second time in the last week.
I told you I'm tired tonight.
I am too. I feel lonely. Any connection?
Any connection? Wow.
No, I'm just
Choose your connection.
I'm asking you if it's just a connection. 56K.
Oh, 56K. We go from T3 to 56K. Boy, I got a lot of ports on me, don't I? Okay, so we'll send those packets out, and they get the information from those adjacent neighbors, right? Then they will be able to say, all right, here's the ports, here's IPs to go into each one. They respond back with what they are, and then they cumulatively come up with this scenario about how big are we? What is our network? What is our contents of our link state protocol? What kind of links do we have? Those links correspond directly with how big they are and how much bandwidth they have. All right. Now, when you flood your neighbors on broadcast traffic on the network, is that really a good thing? How many times have you run Wireshark and just seen it fill up with IP traffic? A lot of it is this kind of stuff right here, trying to figure out who's who. LSPs are sent out under the following conditions. Number one, once the router initially starts up, it doesn't know who's connected to it or whatever. It says, hi, I'm Scott. Who are you? You all in return, send it back to me, and then I have to sort it out. Or if we change topology, let's say the link that from me to Cole, that T3 line got cut. What's going to happen? I send it out to everyone saying, I can no longer talk to Cole. Routers will use the database to construct a topology map of the network by those responses. It's pretty simple, right? Pretty simple concept. Hi, Anthony. I'm Scott. Oh, I heard something. And then I get the information back, okay? So it can help you develop to get to where you need to go. For example, from R1, if I'm trying to reach the R2 LAN, R2 LAN is going to go through R1 to R2. Oh, the shortest path will be 22. So if I'm getting up here, coming to here, then you got the 20 and the 2, right? You following along with that? So any computer that was trying to get to this router will have a metric of 22. If I'm on R1 and I'm trying to get to R3, what do I have? I have the 5 here and then the second 2 to get into that. Does that make sense now? So if I want to get to the R5 LAN from R1, where do I have to go? I can go R1 to R3 to R4 to R5. Why would we want to do that? Why would we want to come here down? It is, because you got 5 and a 10, right? It's 15. Rather than my 20, which is my direct connect. This must be a 56K dial-up. But anyway, that's how it works. I'm not going to talk about we just did that. Basically, you understand how the shortest path destination, it finds the cost that it's going to take to get through those networks and goes to, or adds all the cost, finds the lowest cost, and says this is the path we're going to take. All right? Once the SPF algorithm has determined the shortest path, these routes are then placed in the routing table saying if I need to go to this network, I've got to go through this path. Here's the advantages for the link state. It builds that map. It can independently determine the shortest path. It's very fast versus the distance vector. The periodic event-driven routing updates, generally that does. And the use of a link state protocol, yes. So, which one would you want to use?
The one with more yeses.
Link state. You want to do link state over distance vector. Okay. Link state, the requirements, you have more memory, you have to have more processing power, and you have to have more bandwidth. So you have the intermediate system to intermediate system, or the open shortest path first. Those are your two link state protocols. Any questions? Have I put y'all to sleep? Well, guess what? You're one chapter away. Now we're going to talk about OSPF. Talk about the background and basic features of OSPF. We're going to identify and apply the basic OSPF configuration. We're going to describe, modify, calculate the metric used by OSPF. And then I may talk a little bit about the DRB DRs. And then we're going to talk about additional configurations of OSPF. All right, background of OSPF. It began in 1987, and we're now currently on RFC 2740, which was developed in 99. All it does is it contains a header, it has a router ID and the area ID, because in OSPF we call it an area. Okay. You can have a data link frame header that contains the source of MAC address, just like we've talked about many times already this time. But here's what types of packets you're going to have. You're going to have a hello packet, database description, link state request, link state update, and a link state acknowledgement. What happens? Well, we send out the hello packet just like we talked about a few minutes ago, and it comes back and tells us all this information about it, but we also pass information. We also say which one is my designated router, my backup designated router, and here's the list of all my neighbors. What's the difference between a designated router and a backup router? What do you think?
Well, the designated router is going to probably get the packets by default, and that router would fail backup router.
Very good. Designated router is responsible for updating all other OSPF routers. If it fails, you have the backup. What is the purpose of a link state update? Hello, if something needs to be updated, this link went down, here's what it is. If I have new neighbor or new updated path cost, let's say I took the T3 line and we bumped it to a T5 line. I would do a new link state advertisement saying, boom, we now have a T5 instead of a T3. Now you're never going to see a T5, but unless you want to say you have a T3 and two T1s. Just kidding. Y'all actually got the joke. OSPF algorithm. The routers build and maintain a link state database containing the LSA information received from the other routers. So once we come up and say, okay, Lee, what type of link is between us? and get the packets back from him saying, okay, I'm the designated router, and he understands that, he's going to send me the information saying, here's what I am. So then I take it and develop the cost with the algorithm and say, okay, to get to Zachary, am I going to go through Brent? Am I going to go through Kohler? Or am I going to go through Lee? Default administrative distance for OSPF is a 110. OSPF authentication. The purpose is to encrypt and authenticate routing information instead of it being public text or clear text. This is an interface specific configuration to where I can enable my default encryptions. Okay, we'll get to that encryption here in a few minutes. The topology for this chapter is a disk. You'll see this a little bit. Since OSPF is a classless routing protocol, the subnet mask is always configured in. So what are we going to do? Here's the command for OSPF. Router OSPF process ID, and then give it its process ID. It's going to be the number between 1 and 65,535. It doesn't mean that it has to match any other OSPF router, unlike EIGRP, where you have to get that number from ICANN, remember? That'll wake me up. Now, here's where we have fun. For the network, we have to put in a wildcard mask. Basically, it's the subnet mask, subtract the subnet mask from the 255, 255, 255, 255. And that's your wildcard mask. The area ID refers to an OSPF area. It's basically the area in which all these routers share the same routing information. Okay? So you'll have network, the network address, the wildcard mask, not the wildcard ask, area, then area ID. Okay? The router ID. It's an IP address used to identify a router. The IP address is configured with OSPF router ID command, and it takes precedence over the loopback and the physical interface addresses. If router ID command is not used, then the router chooses the highest IP address of any of the loopback addresses. So this is where you will dictate what your router is. Alright? So if you're looking for OSPF 1, it's going to tell you on each one of these routers what its IP address is. So, for example, this one is saying OSP1 on R1, its port is going to be .5. Then this one would be a .9, and this one's going to be .10 going back up to here. Interface loopback addresses. This is where you can assign a loopback address if you need to. I love how they screw these syntax up. It's router OSPF space process ID, or router space IDIP space, or router ID, or router space dash ID space IP dash address. And if you don't want to use OSPF anymore, you have to say clear IP OSPF process. Okay. Verifying OSPF is going to tell you the neighbor adjacency. If there's none, the router ID's information is displayed. And stated full is not. The consequences of no adjacency, that means no link state and information has been changed. There's no SPF. And I'm not talking about the sunscreen. Few of you got you. You got that one. I must be halfway asleep or halfway awake. Displays OSPF process ID, which is what IP protocols will do. Router ID, network router, advertisements, administrative distance. Show IP OSPF gives you pretty much the same information except area information and last time SPF was used. And then OSPF interface will display the dead intervals. You can also go through the show IP route and it gives you everything in the table, right? OSPF uses a cost to determine the best route. The cost is based on the bandwidth of an interface. Cost is calculated by using 10 to the 8th divided by the bandwidth. Okay? So, if I have a fast Ethernet, which is considered 100 gig, or 100 meg, it'll give you a default of 1. If it's Ethernet, you get 10. If it's an E1 line, it's 48. T1 line, 64. Then you start getting into the modems. 128K, 64K. Do you really want to take something on a cost of $17.85? You'd rather have it on fast Ethernet, wouldn't you? And so that comes into play here when I'm using 64 meg, 128 or 256. Which one am I going to go to? If I'm sending something across, looking at this, I'm actually probably will send it this way. It'll be cheaper cost. All right. Most serial links will default to 1.44 megabits. ISP or IP OSPF command or a cost command will give it a specific cost. So if I say interface serial 000, bandwidth 64, I've just set it to 64 kilobit interface. Or I can say IP OSPF cost and give it a specific cost if I want to. All right. I'm not going to talk about multi-access networks. You don't need to know it. Again, the DR has the highest OSPF interface priority. So who would that be in this room? Everyone got up and started looking at me. BDR, the second highest priority. Who would that be? Kristen? She's the female in the room? She's the boss, right? If OSPF interfaces priorities are equal, then the highest router ID breaks the tie. The timing of the BDR or DR-BDR occurs once the first router is enabled on a multi-access network. When a DR is elected, it remains the DR until one of the following occurs. The DR fails, the OSPF process or the DR fails, or the multi-link interface on the DR fails. So once you get named king, you're there indefinitely. And then we start talking about the U.S. government elections, right? Manipulating the election process. If you want to influence the DR and BDR, boy, aren't we talking about, never mind. Then do one of the following. Boot up the DR first, followed by the BDR, and then boot up all the other routers. Or shut the interface down on all the routers, followed by a no shutdown. Then do the BDR, and then all the other routers. Which would be easier. I would boot up all the other ones first. Go into no shutdown on every interface. So how do you manipulate it? You use the ISP or IP OSPF priority interface and give it a number, 0 to 255. 0 means the router cannot be a BR or DR or BDR. 1 is the default priority. Then we start getting back into the IP routes, the static default routes. Remember, if you're going to propagate that IP route, you have to say default originate, right? Or default information originate. So if we're going to fine tune the OSPF, what are we going to do? We're going to use the autocost reference bandwidth command, and we'll set a bandwidth to it. We can also set the hello interval and the dead interval seconds. Why would you not want to set the hello interval less than 5? You never get anything done on your network because you're flooding it with broadcast. And every 20 seconds you check to make sure that links are still good. All right? Any questions? No questions? Items, concerns, scraps, amongst complaints? Yes, Jackson.
On assignment 9, it doesn't give you the number of posts you need for each one of the lands.
Yeah.
I looked it up. I got the main.
Uh-huh. I haven't looked at it. Once I look at it, then I can put out the information if it needs it. But thank you for bringing that to my attention. Any questions?